To start off with, we've got the octet rule, and in essence, that just means that elements tend to bond in such a way that an atom has 8 electrons on its valence shell. For us, valence only means the outer, so valence shell means outer shell of an atom. If valence electrons are used in like an exam question, it just means the outer electrons, the electrons that are on the outer shell. Atoms with an atomic number below 20, that's just something you need to know, but you don't need it in your definition. However, there are exceptions to the octet rule, and I'm going to go through these. Hydrogen and helium can have up to 2 valence electrons. That's all you need to know. Because of their one shell, and the first shell of an atom has a maximum of 2 electrons. Lithium, very similar to hydrogen and helium, has 3 electrons. So imagine losing its second shell because it loses its valence electron. It has a stable first shell. Aluminium and boron can function well with 6 electrons. This is just something you need to know because, especially in high-level IB questions, they like to trick you if they ask you to find the molecular shape. Or the shape of something, and so keep in mind that aluminium and boron can have up to 6. Sulfur, silicon, and phosphorus, extremely common in IB questions. Sulfur can have up to 12 valence electrons, silicon 12, and phosphorus 10. Keep in mind the red ones as well. Xenon can have up to 12 valence electrons too. These are the most common examples we can see in IB questions. This is all extremely helpful in what we're going to go through next, which is molecular geometry. What are molecular geometries? Well, they simply are the shapes of molecules, the geometries of molecules. By the end of this video, you'll be able to find the shapes of water, ammonia, ammonium, salt. What else is there? Any geometry, to be honest. I'm going to go through everything on the standard level and high level IB chemistry spec. A-level students can revise on this too because I know it's common on your spec as well. So the first geometry we have in the standard level spec is linear. The number of electron domains, firstly electron domains being how many bonded pairs of electrons are there. So a bonded pair means that there are 2 electrons being shared, for one from each atom. And so every 2 electrons, you get 1 electron domain. You can see the 2 lines coming out of the central atom. The bond angle is 180 degrees, meaning because there are no lone pairs of electrons, it's just a straight line. The basic structure of a linear geometry linear molecule is AB2, and some examples are BeCl2 and CO2. The second geometry we've got is trigonal planar. I like to think trigonal planar looks something like a fidget spinner. Something it's really great to find visual things that help you remember certain facts, certain pieces of information by. So I'm thinking a fidget spinner here. The number of electron domains are 3 because we can see 3 lines, 3 bonds. The bond angle of trigonal planar is 120 degrees. Everything I'm saying now, nothing is going to be given to you in your exam. You're going to have to memorize everything. Extremely important. And that is what a trigonal planar geometry looks like. The basic structure of the molecule is AB3. And some examples are BF3 and NO3 minus. The minus being you've got an extra electron, hence the charge becoming negative. The third geometry we have is tetrahedral. Tetra being 4. So in I think it's Latin or Greek, so that's something to help you memorize the structure by. I'm drawing out the basic shape of the molecule. Over here we've got, that just means going behind, and that means going forward. Just remember that for if you had to draw a diagram in your exam, because this makes it more 3D, easier to understand by. There are 4 electron domains, and so the bond angle is going to be 109.5. Again, just memorize that. They're not going to give it to you in your exam. The basic basic structure of the molecule is AB4, and some examples are CH4 and NH4+. Again, just memorize everything here. The next geometry we've got is V-shaped. Another way you can call it is bent. So I will always keep it in brackets when I put my answer in the exam, because you never know which one the examiner's going to credit. So the geometry of this is trigonal planar. So firstly, the difference between geometry and shape. I can't even say it. Geometry and shape. Geometry is the theoretical structure. The shape is the actual structure. So the geometry is trigonal planar because you can see 3 electron domains, including the lone pair. But the shape is bent because you have that lone pair. So the bond angle is going to be less than 120 degrees, not exactly 120 degrees. And if you want to really know the maths behind that, 120 minus 2.5 degrees. So every time you have a lone pair, you subtract 2.5 from your, let's say, the original angle. So 120 minus 2.5 for that one lone pair is 117.5 degrees. And the basic structure of that molecule is AB2E, E being one lone pair. An example of this will be NO2. The next geometry we have is... Why is it saying so long? Okay. Trigonal pyramidal. Very similar to trigonal planar. Same rules apply, just different geometry. So the geometry of this instead is tetrahedral. Why? Because the theoretical shape of this molecule is tetrahedral. So I'm drawing again the diagram of this molecule. Remembering that the individual lines mean to go back and the coloured in triangle just means to go forward to make it a 3D structure. The shape of this with the lone pair is trigonal pyramidal. No? Yes. Trigonal pyramidal. Because the geometry is tetrahedral, you've got a lone pair of electrons, the shape is no longer tetrahedral, the shape is now trigonal pyramidal. And that just means there are 4 electron domains, just like in the geometry that's tetrahedral. The bond angle is not going to be 109.5 directly, it's going to be less than 109.5 because, like I've said earlier, 109.5 minus 2.5 degrees, which is because of that lone pair of electrons. It all means that because of that lone pair, you've got more repulsion. So the angles get smaller because more energy is pushing. Like those 2 individual electrons are pushing the rest of the bonds to go closer together. So it actually is 107 degrees, and the actual structure of the molecule is AB3E, E being one lone pair of electrons, and an example of this is NH3, which is ammonia. The next geometry, and I also think is the final geometry on the standard level spec that I'm going to go through now, is V-shaped bent. So there are 2 V-shaped, like I've said, there's one before as well. You're just going to have to memorize this again. So if the geometry is tetrahedral, and I'm going to draw out the diagram now, and you've got 2 lone pairs of electrons, it cannot be trigonal pyramidal because you have 2 electron lone pairs. You don't just have 1. So the geometry is going to be tetrahedral, but the shape is going to be V-shaped because those 2 lone pairs are pushing the other 2 bonded pairs closer together. 4 electron domains, bond angle being less than 109.5. Here's the maths again, remembering minus 2.5 per lone pair. The overall structure of this molecule is AB2E2, E2 being 2 lone pairs of electrons. Everything I'm doing in pink highlighter, it's just a basic structure you should know for if exam question shows a molecule, and this is actually a good revision technique or a good strategy to help you identify the geometry. So next we're going to go through molecular geometry higher level and for the IB spec. A-level students who are watching, if this isn't on your spec, you can completely skip past this. I don't want to confuse you even more. So the first geometry we've got in higher level spec is trigonal bipyramidal. So these are all extensions from the previous standard level spec we've just gone through. So this is the shape of trigonal bipyramidal. Overall, you've got 5 electron domains. And the bond angle is going to be, there's actually 2 bond angles here, 90 degrees and 120 degrees. I had terminology for this. Oh yes, so the horizontal lines that the first time I circled, that just meant equatorial position, and then the second time I circled was axial position. So here I'm writing out 5 bonding pairs, therefore 5 electron domains. The bond angles, and you will have to memorize this again in high level. They're not going to give this to you in your exam. 90 degrees and 120 degrees. The structure of this is going to be AB5. And all in trigonal pyramidal, these are actually, the ones in colour are subcategories within trigonal pyramidal. So the next version of trigonal pyramidal, let's say, is seesaw. The bond angles are 90 degrees, well, less than 90 degrees and less than 120 degrees. I don't know why my arrow is the wrong way around. So there are 4 bonding pairs plus 1 lone pair. So overall, 5 electron domains, meaning the geometry is trigonal pyramidal, but the shape is seesaw because of that 1 lone pair. The bond angle here, there are 2 bond angles, and the first one is, yes, less than 120 degrees, and the second one is going to be 90 degrees, which I've written the other way around again over here. Just memorize this in your exam. Seriously, that's the only way you're really going to benefit. And because they are, in fact, less than 120 and less than 90 degrees, what did we say before? Every lone pair, you subtract 2.5 degrees from its original overall bond angle. You don't need this really in your exam. You can just write your bond angles to be less than 120 and less than 90, but in case you wanted to know the maths behind it. The overall structure of this is going to be AB4E. What colour am I going to choose now? I went for blue, apparently. So the next trigonal bipyramidal geometry version, let's say, is T-shaped. That's what T-shaped looks like. And you have 2 lone pairs this time. So the bond angle is going to be less than 190 degrees. So we've got 3 bonding pairs of electrons plus 2 lone pairs of electrons. The geometry is going to be trigonal bipyramidal because 3 plus 2 is 5 electron domains. The bond angle is less than 90 degrees. Now this is what the textbook says. I'm going to explain this later, but I'm not sure if the 2 lone pairs create that 180 degrees. I'm not sure if they actually cancel out to create a straight line. The IB textbook literally just says less than 190 degrees, so I'm going to say follow that for the bond angles. And the overall structure is AB3E2. We've got one more underneath the category of trigonal bipyramidal, and that simply is linear. And what does linear mean? So over here, you've got 2 bonding pairs of electrons and you've got 3 lone pairs of electrons. So 2 bonding pairs plus 3 lone pairs creates 5 electron domains. Again, that geometry is trigonal bipyramidal, but because of those 3 lone pairs of electrons, your shape is going to be linear. IB, this is a lot for the high level students. I'm doing high level right now. This is a lot to memorize. I'm going to say you've got until next year if you're in year 12. You've got until next year. Please just try and memorize these for your exams. The bond angles are 180 degrees because the lone pairs actually cancel out. Repulsion isn't, there's actually no repulsion here, because they're both pushing against each other. They're all pushing against each other equally with the bonding pairs, hence the linear shape. If that makes sense. If that doesn't, comment down below, and I'm just showing you everything we've gone through with the high level trigonal bipyramidal spec so far. Same thing as trigonal bipyramidal, we've got octahedral, but we also have subcategories within octahedral. So the first version of an octahedral geometry is the octahedral shape. And did I draw that right? Yes. So yeah, octahedral shape simply means 6 electron domains. In between the bond angles are 90 degrees. 6 bonding pairs of electrons, therefore 6 electron domains, therefore the bond angles are 90 degrees. I'm just writing everything out in clear for you. And the geometry is octahedral. So the overall structure of this molecule will be AB6. 6 octahedral. Within octahedral, you have another version, a subcategory, which is square-based pyramidal. That simply means you've got 1, 2, 3, 4, 5 electron domains and 1 lone pair of electrons. The bond angle will be less than 90 degrees. I should have wrote that. Less than 90 degrees because we have those 2 lone pairs of electrons. So you've got 5 bonding pairs plus 1 lone pair. That makes 6 electron domains. So the geometry is octahedral. However, the shape will be square-based pyramidal. The bond angles are less than 90 degrees. Put a little less than sign next to it because we have those 2 lone pairs, that 1 lone pair, those 2 electrons. And the overall structure of this molecule is AB5E. That being 5 bonding pairs of electrons and 1 lone pair of electron. And I think it's the final version of octahedral is square planar. And that simply is 4 electron domains and 2 lone pairs of electrons. So in between those bonded pairs, you've got 90 degrees. So you've got 4 bonded pairs of electrons and 2 lone pairs of electrons. So 6 electron domains, geometry, octahedral, shape, square, planar. Oh, okay. Bond angles. I'm following what the IB textbook is sharing with us right now. When I said less than 90 degrees, you're going to have to look up on that because the textbook does not specify. Maybe in your exam, you're not going to be asked what the bond angles are, like the bond angles are of octahedral, but it's good to keep it in mind. So I'm going to say do some extra reading on octahedral for the bond angles. The textbook isn't really saying what they are. And I'm just going through everything that we've done so far. I can't emphasize this enough. You really need to memorize everything I've included in this video so far. Everything here is going to be extremely important to you in your exam, as I've said before, and they're not going to give you this in your data booklet. I'm actually going to give you some exam questions now to do for revision, and feel free to pause the video and come back and watch my solutions to mark it with. So the first question is carbon tetrachloride, CCl4. I want you to tell me the geometry, the number of electron domains, the shape, the bond angles, and draw the Lewis diagram. So the first thing I'm doing here is writing the number of valence electrons of each element included. So this makes it extremely clear to us in our exam what we're actually working with. Carbon has 4 valence electrons because it's in group 4 of the periodic table, hence chlorine having 7, being in group 7. I'm circling tetra because I think it's Greek or Latin, but tetra means 4. So keep in the back of your head, the geometry is tetrahedral and the shape trigonal pyramidal. They're the only tetras we actually work with so far. I'm drawing a ball and stick diagram here. This is not a Lewis diagram, just to give us a vague idea of what the molecule actually looks like. We can see from here there are 4 electron domains, 4 lines coming out of the central molecule. So every 2 electrons, as I said before, is 1 electron domain because one is being shared by both sides. So the geometry is tetrahedral because of the 4 electron domains. We can also see that there are no lone pairs of electrons, so the shape has to be tetrahedral too. And I'm writing down again, the shape is tetrahedral. Therefore, the bond angle, as we've said previously, is going to be 109.5. Something you just have to know. And I'm drawing the Lewis diagram below. Remember that dotted broken down line is to go back and the coloured in triangle means to go forward, just to make it a 3D diagram slightly. And remember the bond angle is 109.5, and always remember in Lewis diagrams you have to draw all of the valence electrons. Even if it's not the central molecule, chlorine, you have to show that there are still 6 electrons not bonded, 6 valence electrons of chlorine elements. The second question I'm going to give you is ammonium cation, which basically is NH4 plus. Ammonium being NH4 and cation being a positively charged ion, meaning you've lost an electron. I'm going to follow the exact same process as I did in the previous question. The process of how you how you find the molecular structures and geometries is exactly the same for every single molecule you'll be given in an exam. It's just a matter of figuring things out, really. So I've done nitrogen, 5 valence electrons, and hydrogen 1. Drawing the ball and stick diagram now. Remembering that NH4 is a cation, so you've lost an electron. There are actually 4 valence electrons for the nitrogen. So we can see here 4 electron domains, and so the geometry is tetrahedral. And again, I'm just supporting the fact that it's a cation, so you've lost an electron. Because if you count the number of dots by n, there are only 4, not 5. And always remember to put the brackets with a plus. Similar to how the molecule is actually written out, you'll get discredited if you don't do that in your exam. And the third thing I'm doing is writing down the shape. So obviously no lone pairs, meaning the shape is also tetrahedral. And the bond angle will be 109.5. 109.5 degrees. I'll draw the Lewis structure below. So we've got N, we've got H going back. We've got H going forward. And we've got another H, obviously bonded. And I'm writing the bond angle, 109.5. I didn't. And this would mean I would have got discredited in the exam. I didn't put the brackets with a plus. Remember how, as we did in the ball and stick diagram, include those brackets and the plus to show it's a cation? The third question I'm going to give you is nitrogen trifluoride. NF3. I'm going to repeat the exact same process as I've done for the previous two questions. Nitrogen has 5 valence electrons. Fluorine has 7 valence electrons. And I'm going to write that. Drawing the ball and stick diagram now. Trifluoride. Look at the tri. Another Latin Greek word for 3. And you can see in NF3 there's also 3 fluorines bonded. So keep in the back of your head now, trigonal or trigonal planar. So we can see there are... Actually, no, do not keep in the back of your head. Do you know why? Because there are 4 electron domains. This is a question that might trick you in an exam. You may think it's to do with 3, but actually it's to do with 4. There is 1 lone pair in nitrogen trifluoride. The geometry is going to be, and I'm going to write that down. Well, first I'm writing there are 4 electron domains. So the geometry has to be tetrahedral. This is a sneaky question. The geometry is tetrahedral. But that 1 lone pair means that our shape of the molecule is going to be trigonal pyramidal. Remember, tetrahedral, if you have 1 lone pair and the geometry is tetrahedral, you've got a trigonal pyramidal shape. And the 5th thing I'm going to do now is just draw the Lewis structure. Seeing that the lone pair is at the top. I didn't draw the valence electrons for the fluorines. That was going to take long in this video. But remember in your exam, keep the unbonded electron, show every single valence electron that is in the molecule. That 1 lone pair, therefore the bond angle is 109.5 minus 2.5. What did I say before? Every time you have a lone pair of electrons, you subtract 2.5 for every 1 lone pair. So 109.5 being the original bond angle, subtract 2.5 and you get 107 degrees being the bond angle in trigonal pyramidal. But in your exam, you don't really need to do that. So you can just write less than 109 degrees. I'll give you one last question to practice. And this one is going to be sulfur difluoride, SF2. So step 1, the valence electrons. Sulfur has 6, fluorine has 7. Step 2, the ball and stick diagram. Showing the electrons that are shared. But look, if sulfur has 6 valence electrons and it only shares 2, you've still got 4 valence electrons. You've got 2 lone pairs, 4 electrons that aren't being bonded with the fluorines. So if we look now, we still have 4 electron domains because 2 electrons are being shared. So you can see that dot and X, there are 2 of those, 2 electron domains, and there are two lone pairs on top. So the geometry will be tetrahedral, but because of those two lone pairs, your shape is going to be V-shaped. In brackets, bent. Because I know some people call it different things. The fifth thing we're going to do is just draw the Lewis diagram. I just drew the dot and cross just to show. Actually, you could call it a dot and cross diagram too. It's not really Lewis. I haven't done the valence electrons on fluorine. But look at the first question that we've gone through. It's self-explanatory how the Lewis structure would actually look. The bond angle is going to be now 109.5 minus 2.5 minus another 2.5 because we've got two lone pairs, which is 109.5 minus 5. And so the bond angle is actually 104.5 degrees. But remember, in your exam, you won't really need to write 104.5 degrees. You can just write less than 109.5 degrees, like I've done in the diagram.